Hello everyone, and welcome to today's session in the PML School. My name is Chris Mehl. I'll be your host for today, and we'll be discussing the example PD4 from Gabrielsson and Weiner. This is an IV bolus model of warfarin with a turnover model, including a T-leg. Just as sort of an opening announcement, if you look on the right side of the WebEx, there's a chat and a Q&A. So if you have any questions during the presentation or during the software demo, feel free to go ahead and type a question in the Q&A, and we will respond to some selected questions, time permitting, during the presentation. And of course, at the end, we will address all questions on the Certara forum. So a bit of a background of today's example. We're using warfarin. Warfarin is often prescribed as an anticoagulant, and it acts indirectly to prevent blood clotting by inhibiting the production of reduced vitamin K that's involved in the formation of the prothrombin complex, as shown below. So there are some precursors for the prothrombin complex, and the conversion to the active prothrombin complex is mediated by reduced vitamin K as well as gamma-glutenyl decarboxylase. And so warfarin actually inhibits the formation of reduced vitamin K. It acts both on the vitamin K epoxide reductase as well as on vitamin K reductase. So this inhibits the production of reduced vitamin K and reduces the formation of the prothrombin complex, which downstream leads to clotting. In this example, our response will be the activity of the prothrombin complex. Okay, so if we do an exploratory plot, we have the PCA activity on the y-axis and then time in hours on the x-axis. We see that the PCA goes down over time, and then it increases back toward the baseline. This is following an IV bolus dose of warfarin. The response is measured as percent of the PCA activity, where normal is 100%. As far as the pharmacokinetics of warfarin are concerned, the warfarin PK is well characterized from previous studies. It follows a one-compartment model, and after bolus administration, we have the microconstants volume of distribution and elimination rate constants, and we will use these for the PK parameters in the following equation. So the concentration of warfarin equals the dose divided by the volume times e to the minus ke times time, where the dose amount is 1.05, volume of distribution is 1, and Ke is 0.0228. The objectives of this study are to use an indirect response model for the warfarin PCA interaction. We will elaborate on a model with and without a lag time in the dynamics, and compare the two models by AIC as well as parameter precision. Time permitting, may cover an extension of the model to a precursor pool model. Okay, so to describe the warfarin by an inhibitory function, we'll go ahead and derive this. The empirically found inhibitory function of warfarin on the synthesis rate of PCA, assuming Imax equals 1, is as follows. So the inhibitory function equals 1 minus c to the gamma divided by IC50 gamma plus c gamma. If we then substitute for 1, if we substitute IC50 plus c over IC50 plus c for 1, we get a subtraction with two like denominators. So the concentration terms cancel out, and we're left with IC50 divided by IC50 plus C. If we then divide the numerator and denominator by IC50, we get 1 over 1 plus C to the gamma divided by IC50 to the gamma. And then we can get the final form here, where we just get C divided by IC50 all raised to the gamma in the final inhibitory function. Okay. For the turnover model, the turnover rate of PCA is adapted from the base inhibitory turnover model, which is Kn times the inhibitory function minus K out times the PCA response, where Kn is the rate of production and K out is the rate of loss. At baseline, the response at time 0 equals Kn divided by K out. Therefore, Kn equals R0 times K out. What we'll do to write the turnover model, we'll set the response at time 0 equals P0, then substitute P0 times K out for Kn. So the differential equation for PCA becomes P0 times K out times the inhibitory function minus K out times PCA. This in turn rearranges to K out times P0 times the inhibitory function minus PCA. Okay, so with these models, we typically start with initial estimates for the fitted parameters in the model. And so an example of finding an initial estimate for K out, if one plots the PCA on a log scale versus time, the onset slope here is an estimate of negative K out. So our K out estimate will take the natural log of the PCA at time 0 minus the natural log of the PCA at time 24 divided by 0 minus 24. And this results in an initial estimate of K out of 0.03. Okay, for the IC50, that's another parameter in the turnover model. And if you look at the original exploratory plot, the time of IC50 occurs when the response recovers by 50%. So this is in the offset portion. So this time, to get an estimate for IC50, what we'll do is we'll solve the warfarin concentration function at time 80. So remember, our concentration of warfarin equals dose divided by volume times e to the minus ke times time. So if we insert our amounts, our dose amount 1.05, our volume is 1, ke is 0.0228, and then the time point is 80, the initial estimate for IC50 will be 0.16. Okay, so a summary of the initial estimates in the turnover model, the P0 is the baseline PCA activity, and that's 124. That's coming from the input data set, the response at time 0. The K out is 0.03, derived from the onset slope in the exploratory plot. IC50, warfarin concentration when response recovers by 50% is 0.16. And then our last parameter is N, that's the gamma exponent, which can be found by fitting a built-in inhibitory indirect response model. And we'll see that an initial estimate of this will be 4. Okay. In Phoenix, there are some built-in indirect response models. So based on the mechanism of action of warfarin, this example is inhibition of production. Okay, so in the built-in mode, one can select PK indirect. For the PK portion of the model, we'll use microparameterization. It's an intravenous bolus dose with one elimination compartment. And since the PK is well characterized, what we can do is use the freeze PK option and set the PK parameters as constants in the model. And then to specify the turnover model in built-in mode, we'll select inhibition limited of buildup. And then toggling the exponent on will introduce gamma into the model. So this is the PML code that's written for the built-in model. Okay. As we've alluded to in previous presentations, Phoenix does have a graphical mode for interfacing with the models, where this is the PK model, and then this is the indirect response effect model, where PCA is the observed effect. We're actually not going to cover the graphical mode in this particular example. It's more convenient to work in the text mode, but there are several other examples of the graphical model that have been presented previously in the PML School series. Okay, so for our base turnover model, this is the PML code. This is when editing the model in text mode. And this is annotated. So all of the statements that you see in green are comments indicating what the segment of code does. So at the beginning we have a dose point, A1, that's the dose delivered to the central compartment. The initial concentration of warfarin equals the amount in the central compartment divided by the volume of the central compartment. The differential equation for the simple one-compartment IV bolus model expressed in amounts, it's the amount equals minus KE times A1. As discussed in the introductory slides, the inhibitory function of warfarin is 1 divided by 1 plus CW divided by IC50 raised to the power N. We then set the initial value for PCA to P0. You can think of this as a baseline parameter. So that's using the sequence statement. We say PCA equals P0 at the start. Then the differential equation for PCA, we showed the derivation in the slides. The PCA equals K out times P0 times the inhibitory function minus PCA. The next segment contains the observation. So this is observed PCA with additive error term. So PCA odds equals PCA plus epsilon. The PK parameters for warfarin will be declared as frozen fixed effects. So that's where we have the fixed effect, the name of the parameter, volume, and KE. We use the freeze statement to say that these values will be constant. So for V we have 1, KE 0.0228. And then lastly, the fitted parameters for the turnover model are expressed as fixed effects with initial estimates. So these are fixed effects. We have IC50, gamma, K out, and P0. Okay, so this is the first model that we will fit. There's a second model where we will introduce a lag time. So the lag time it accounts for the lag in the onset. Okay, so the warfarin PK and the inhibitory function are the same as in the previous slide. To add a time lag to the model, we'll declare a double precision variable named flag. And this is a time switch for the turnover model function. Okay. Next, we have a sequence block where we have initial PCA with the on and off switch, which is the flag variable. So in our sequence statement, we say the initial PCA equals P0, and initially the flag is set to 0. We'll use the sleep statement. So the sleep, nothing happens with this block for a duration of T lag. So this is a lag time that is a fitted parameter in the model. Once the T lag time has elapsed, the flag switches to 1. And so then where do we use the flag? The flag gets used in the differential equation for PCA. So this is the same differential equation for PCA as in Model 1, and then it's multiplied by the flag. So during the lag time, the flag is 0, so PCA is 0, and then it simply switches to a 1, multiplied by 1. Okay. We also have our observed PCA with the additive error model. PK parameters is frozen fixed effects as before. And then the turnover model, these are going to be the fitted parameters declared as fixed effects with initial estimates. And they're the same initial estimates as in Model 1. We've added the T-lag parameter with an initial estimate of 1. Okay. At this point, I'd like to switch to the demonstration portion. So I'm going to switch to the Phoenix application. Cheryl, can you see my screen okay?
Yes.
Thank you. Okay, so we have the data So this is the time course and the observed PCA. Okay, and here is an exploratory plot where we show the prothrombin complex activity versus time. It follows the typical inhibitory profile. Okay, so I'm going to start by showing how to use the built-in model. I'm going to send the input data set to Phoenix modeling and then a Phoenix model. And I'm going to call this the built-in indirect response model. Okay. And at this point, we'll go ahead and set the structure of the model. There's only one profile, so we'll toggle population off. Set the type to PK indirect. For the PK model, the parameterization is micro, and it's an intravenous bolus with one elimination compartment. I'll go ahead and check the freeze PK checkbox. So these are frozen PK parameters. And for the indirect model, this is going to be inhibition limited of the buildup with an exponent term. And as you can see, when you use the built-in mode, the nice feature of this, over to the right are the PML statements, and they get updated as you make these model selections. So toggling on exponent adds gamma to the concentration term. Okay, we'll go ahead and map PCA as the effect variable, and then enter dosing using an internal worksheet, 1.05 for the amount at time 0. And then lastly, we'll use the parameters tab, fixed effects subtab to put in the initial values for the parameters. So these are frozen. Freeze PK was selected. For KE, it's 0.0228. The estimate for K out is 0.03. For Kn, the response at time 0, if we look at the input data set, is 124. So if we multiply 124 times 0.03, which is the estimate for K out, we get an estimate for the Kn, which will be 3.7. Imax is 1. And IC50, we discussed that, 0.16, an initial estimate here. And for the initial estimates for gamma, we can switch to the initial estimates tab. Okay, I'll start with my time course, which is 150. And I can visualize different values for gamma. So as I increase gamma, I get some sigmoidicity and capture the lower points here. I'll go ahead and bump this up to, say, 3. Use 4. Okay. So this is my initial estimate for gamma. And then this will be fitted when the model is run. Back to the parameters and fixed effects. I'm now ready to run the indirect response model. Okay, and in the indirect response model, let's see, these are the fitted parameters for the indirect response. And for the gamma did converge at around a value of 4. So we'll use this as an initial estimate for gamma for the text models. Okay, so at this point, I'm going to go ahead and run the text model that we discussed in the slides, the first turnover model, number 1. We'll send this to Phoenix modeling and then Phoenix model. I'll call this 1 turnover, base turnover model. Okay. I'll go ahead and toggle off population. And then for the model text, I'm going to switch to edit as textual. So edit the model as textual. And then the model code is in this, this code statement here. So we discussed this in the slides. I'm simply going to copy and paste the model text into the Phoenix model object. Okay. And the statements here are the complete text model, and they include the initial estimates for the parameters. I will need to enter the dosing. So A1 is 1.05 at time 0. And the warnings tab will give me a clear message of what's missing. So in the model, we declared the response as PCA obs. So that tells me that I need to go back to the main setup and map PCA to PCA obs. Okay, and that's all that I need to do in terms of the setup. Go ahead and run the base turnover model. Okay, and I will check to make sure that I got some final fitted parameters, and did, as well as the fitted plot. So this is the fit for the base turnover model. And you can actually, if desired, let's increase the width a little bit. You see in the fitted plot, the model, the fitted profile looks pretty good, although it did overestimate some of the points in the onset here, particularly near the maximum. Okay. All right. Next, I will go ahead and add a lag time on the response to see if this fit can be improved. So I'm just going to simply copy the base turnover model and paste it back into the workflow, and call this model number 2, base turnover model with T-lag. Okay, and for the model text, we'll get this turnover model. This is the one that has the on-off switch where we sweep for T-lag and fit T-lag as a parameter. Okay, so I'll come back into the setup model and paste the lag time model text. Since I copied the model, it remembers the dosing, the main mapping, so I don't need to do anything else here. I can simply run this updated text model. Okay. Check my output thetas to make sure that fitted parameters were found, and also look at the fitted plot. So on the fitted plot, you see that the onset and the minimum, it did a better job of fitting on the profile. And what we can do is actually compare some of these results. There's a handy tool called the append worksheet. So we'll start with the overall. I'm going to take the overall from the base turnover model and send it to data and then append worksheets. Rename this object to append overall, and select some source columns. So -2 log likelihood, Akaike, Schwartz, and number of parameters. Then for worksheet 2, we'll go ahead and take the results from the second model with the T-lag and use the same input columns, and then go ahead and run the append. Okay, so this gives a nice comparison of select diagnostic outputs we see that adding the t-lag has reduced the diagnostic parameters. The log likelihood went from 58 down to 49.9. Akaike went from 68 down to 61.9, and Schwartz went from 69.6 down to 63.7. So adding the t-lag did improve the fit with respect to the diagnostics. And also look at the parameter precision. So we'll go ahead and append the theta as well. So we'll take the theta worksheet, send it to data, and then append worksheets. Call this one append theta, where the source columns are parameter, estimate, CV%, and the 95% confidence interval. And then for worksheet 2, go ahead and bring in the theta from the model number 2, including the t-lag, and map the same source columns as before, and then execute. Okay, so these are the combined final parameter estimates for both models. I'm going to actually use this feature in the upper right corner, the sort worksheet, and sort by parameter name. So parameter by parameter we can compare. So the base model for IC50, the values were actually similar, 0.26 compared to 0.235, but the coefficient of variation did decrease, which means that there's more confidence in the estimate for the model, including the t-lag. KE, notice these are 0. Remember, these were fixed constants in the model. The PK parameters were fixed. For the K out, and the value increased from 0.3 in the base model to 0.06 in the t-lag model. The CV% did drop by a little over 1%. The gamma estimate went from 3 in the base turnover model down to 1.5 in the t-lag model, and the coefficient of variation was significantly reduced from 42 down to 13. And then the P0 estimate went from 120.9 in the base model to 122.2 in the t-lag model. And again, the CV% were reduced. And the t-lag model was only present in the second model. So this is the estimate for t-lag, which was 6.5. And then, of course, volume was a fixed constant. So the implementation of the t-lag did improve the parameter precision across the board for the parameters. Okay. So I'd like to go ahead and switch back to the slides at this point. Okay. So a summary of what's been done so far. We went ahead and fixed the PK parameters from a previous study, developed an indirect response model, derived initial estimates, and then fit turnover models with and without lag time to the data. Okay. So these are summaries of the base turnover model results. Again, the downswing here did not model optimally for the base turnover model, although the offset did model nicely. And we saw in the initial parameters here, when we switched to the lag time model, the onset had a better fit visually, and the parameter precision was increased. Okay. Now you may have noticed in the output from the second model with the lag time, it's not obvious where the lag time's entering the picture here. So when you run the Phoenix model by default, you get on the output plot, you get one prediction for every observed point. So there's a predicted point here, a predicted point here, predicted here, and so on. That's why it looks a little bit jagged, because there's only one point at the observed time. If you want to get more predicted points to get a nice smooth fit, what you can do is use the table function on the Run Options tab to set up a simulation table using the sequence statement. Okay, so we go to the Run Options tab and enter a sequence statement. It might be a little difficult to visualize here, but I'll show it back in Phoenix. This is sequence 0, 160, 1, which means that there's a predicted point every 1 hour from time 0 to time 160, where the variable is PCA. And then when you rerun the model, the predicted points will all appear on this table 01 output. And then we can then use this to build an overlay plot, which will show the lag time. So this was fitted to 6.5 hours. Okay. So I'll go ahead and switch back to Phoenix to show how to do this. So I'm now back in the Phoenix application. So I'll go back into my turnover model that included T-lag, go to Run Options, and then click Add Table. The times, we'll use the sequence statement, sequence open paren 0, 160, 1, close paren, and then the variable is PCA. Okay, go ahead and rerun the model. Okay. Go ahead and re-execute my append worksheets since I made a change to the upstream model. This should have no impact on the actual results. I'm just re-executing to refresh the pink color. Okay. And then I'm going to import an overlay plot template. Now we have two data sets. The first data set is going to be the table 01 from the model 2, and then the second one will be simply the observed PD4 data. And I'll go ahead and execute. Okay, so this is the overlay plot where we have the observed PCA, the red circles, and then the predicted PCA with more points. So we have 160 output points, and then you can actually visualize the T-lag goes out to 6 hours here. And this allowed a better fit for the onset here. Okay. All right. So we have a little bit more time here. I'd like to go ahead and cover the precursor pool model. So I'll go ahead and switch back to the slides. So we saw that the adding a lag time increased. For those of you who are fans of more mechanistic models, if we go back to the original diagram here, we see that warfarin actually inhibits the formation of the production of reduced vitamin K, which is actually one step upstream from the formation of the prothrombin complex, which we're measuring as the response. Okay. So the first two models that we covered are the basic turnover model, both with and without lag time. Since warfarin acts one step upstream, inhibiting formation of reduced vitamin K, model 3 is a precursor pool model. So we're replacing the lag time with a transit compartment with its own exit rate constant K1. So we saw the first two models that we did. The base model here, the inhibitory function is acting on the production of PCA. Model number 2, we have the Kn plus T lag, where inhibitory function is acting here. Model 3, the precursor pool model, we actually have the inhibitory function acting on the precursor pool. The transit rate constants K1 times the precursor. And then we have the PCA, and then which is parameterized using K out times response. Model number 4 is very similar to model number 3, except that the K1 is set equal to K out. So we have the same precursor pool, inhibitory function is acting on the precursor pool, and then we're simply substituting K out for K1 here. So we have only one K parameter. Okay. So for model number 3, this is a text representation of the two models. So for model number 3, I'm just highlighting the differences here. So the warfarin PK is the same as we've been using, same inhibitory function of warfarin. We're just simply moving it one step upstream, this inhibitory function. So in our sequence statements, we're setting the precursor pool equals P0 and also the PCA equals P0. Then we're adding a differential equation for the precursor pool. So precursor equals P0 times K out times inhibitory function minus K1 times the precursor. And then the second equation for PCA, which is our response, equals K1 times the precursor minus K out times PCA. Okay, and then lastly, since we've introduced this transit rate K1, we'll declare this as a fixed effect, so a fixed effect for K1. Okay. The second precursor pool model, which is model number 4, again, the warfarin PK is the same, inhibitory function also the same. We're setting the K loss equals K out, loss of the precursor equals K out. Initial conditions, both precursor and PCA are set to P0. And then we have two differential equations, one for the precursor, P0 times K out times inhibitory function minus K loss times precursor. And then the PCA equals K loss times the precursor minus K out times PCA. Okay. I'm going to go ahead and switch back to the Phoenix application and run these two additional models. I'm going to import my model text. Okay. And go ahead and copy model number 2 object and paste it back into the workflow. We'll call this 3 precursor pool model with K1 transit. Okay, and take the model text as discussed from the slides and go to model under setup, paste in the model text, verify that the dosing is entered correctly, and go ahead and run the precursor pool model. Okay. And go ahead and check my thetas, make sure I got outputs here, as well as check the fitted plot. This was model number 3. And I'll make a copy of model 3 and run model 4. This is going to be model 4, precursor pool model, K loss equals K out. And take the model text and apply this to model 4. And go ahead and run the model and verify my outputs were produced successfully, and they were. And remember that we had the comparison, so we can actually add using this handy append worksheet. If I want to add the results from the other models, I'm simply going to start with the overall and increase the number of worksheets to 4, since there's now 4 models. For worksheet 3, I'll take the overall from model number 3 and map my output diagnostics, and then do the same for model number 4. And then execute. Okay. So we can now see diagnostics for all 4 models. The -2 log likelihood was reduced from the base turnover model and is further reduced in the precursor pool models. For Akaike and Schwartz, the model that had the lowest values was actually the precursor pool where K loss equals K out. Okay. And we can also examine parameter precision. So that's in the second append worksheet. Bring in the theta. And also results from model number 4. Okay, and then using sort worksheet, you can sort by parameter name, ascending, apply, and OK. And we'll now get the by parameter all 4 model results. So the IC50 really didn't change a whole lot between these different models. The highest parameter precision for IC50 actually came from the TLAG model. K1 was only present in model number 3. It had a CV percent of 17.7. KE was fixed from the PK. K out increased from the base model 0.03 to 0.06 in the lag time model. And then the precursor pool model actually was able to get a better parameter precision at a value of 0.09 for K out, down to 6%. In the gamma, there was a significant improvement in the gamma parameter by adding the T-lag, and then the precursor pool models further reduced, got better precision for the gamma. P0, this was probably the easiest parameter to fit. Remember, we had an observation at time 0 in the input data set, so having this baseline value was not very difficult to fit. It didn't change very much, and the parameter precision was very high to begin with in the base model, and it did get reduced somewhat in the later models. Okay. So these are the 4 different models discussed in PD4. Go ahead and switch back to the slides. And at this point, go ahead and open up for any questions that you might have. So there's a question here, how did the built-in turnover model compare to the other models? We can certainly take a look at this. Why don't we go ahead back here, and I'll simply add that in my append. So we'll look at the base. So sort of the rationale for why did we add this is because we separated out the inhibitory function for warfarin. Pardon me, I'm going to go back to share Phoenix again. So part of the rationale now here was having the separate inhibitory function for warfarin means that we can develop a more mechanistic model. We can move around the inhibitory function. It's also parameterized using P0. So P0 we can take directly from the input data, so it's easier to fit this parameter. So that can help in the precision. But what we can do is we can add the built-in model results to the append worksheet. So let's go ahead and add a 5th worksheet here where we take the overall from the built-in and let's go ahead and re-execute. So for our built-in model, these are the diagnostics that we got. The built-in model did a fairly good job. It did have a return code of 3. Return code 1 is the best return code that you can get in a fitted model. So the indirect response built-in model did a fair job with the diagnostics, so it suggested that it is correct to use an indirect response model. It did have a return code of 3, which meant that one or more of the parameters, there might be some issues with some of the parameter estimates. And if we go to append theta, we can actually add the base model results from the built-in. And let's go ahead and have a look at these. Okay, and remember to sort by parameter. Okay, so the built-in model, indirect response model, okay. Okay, here's the names of the parameters are different here. These are typical values, and so that's why they didn't show up in the list. What I could do is maybe switch to text mode and get these named the same. But for our K-out, the K-out parameter precision was 13 in the base model. And then the K-out in these additional models, the precursor pool further reduced and got a better parameter precision for K-out. For the IC50, the built-in model had a precision of 8.8%, and then this was further reduced in all of the text models. The gamma had a high coefficient of variation, 26.7, higher than the N parameter in both the lag time model as well as the precursor pool model. So, you know, you can start with a built-in indirect response model and determine whether your precision is good enough, and just use that. If you want to develop a more mechanistic model, as discussed, you can use these text models that were presented here. That was a good. So another question: why does K loss equals K out give a better fit? Okay, so I'm going to go back to Phoenix. This was actually discussed in the Gabrielsson and Weiner reference. So why was there a better fit with Model 4 compared to Model 3? So if we look at some of the results here, let me switch back to model number 3. We had the transit K1 and then K out. These final parameter estimates were actually very close to each other, 0.94 and 0.10. And so these parameters are highly correlated. It's an additional parameter. So the number of parameters in model number 3 is 6. When you actually switch to the model number 4, where K loss equals K out, we only have the 1 K out, which converged to 0.092, and then the N parm was 5 instead of 6. So it's a reduced model, and it ended up having better overall diagnostics as a result. All right. So I think, and then the last question, can the model compare option be used instead of appending worksheets? This particular feature, the model comparer, will only work in population mode. So that model comparer, you need to have an NLME license and run models in population mode to get the model comparer. With individual modeling that's not in population mode, you can simply use the append worksheets. Okay, so I think at this point, we're getting close to the time here. I'm going to go ahead and wrap up the Q&A session. If you have any other last-minute questions, feel free to submit them, and we'll address them via the forum. I do have a few follow-up announcements. So the materials, the models that I presented, the text models, will be made available in the Certara forum. That's here at support.certara.com/forums. It's forum 34 of the PML School. So you can get the model text files as downloads and run them on new data sets. Questions and comments can be exchanged in the forum, or you can also send them to support. Okay, we have the PML School on Twitter is @PML School. Notifications on updates of material, Q&A, and discussions. And then the PML School is also on YouTube at the link below here. I do want to also make you aware that we do have Certara University available. This has a wide range of on-demand and classroom courses. They include introductory, intermediate, and advanced instruction in Phoenix Wind Online, population modeling with NLME, and the IVIVC toolkit. Another course offering is fundamentals of pharmacokinetics and pharmacodynamics, non-compartmental analysis, programming boot camp, as well as some partner lectures and webinar series. So please visit Certara University website for more information. Coming up, the next seminar in this series will be on June 22nd. That's another Thursday at the same time. The presenter will be Dr. Bernd Wendt. He will present PD7 from Gabrielsson and Weiner, which covers turnover model using stimulation of loss at different dose levels. To register for future PML School webinars, please visit the link here at www.certara.com. I'd like to thank everyone for your time and your questions today. This concludes the session, and you may now disconnect.